Good morning, dear student, and welcome to this 35th edition of our numerical method class. Last time when we parted, I gave you homework. I hope you did that. But before we proceed, I will quickly recall what we did last time. So we are currently tackling eigenvalues and eigenvectors of a given matrix. A matrix of an arbitrary size can be very large. In general, because in this context, we assume that the size is so large that you cannot compute the eigenvectors and the eigenvalues manually. So you need to use a computer. So the de facto method, the first attempt, is the power method. In the power method, it's mainly matrix multiplication, but that is matrix vector multiplication. So that is it here in the summary. To summarize, this is what you generate. So this is the sequence that you generate, and you perform a projection. You take the ratio to approximate the Rn, as I mentioned, right? If you look at the algorithm here, this slide, you can see that the approximation of our lambda 1, which is the dominant eigenvalue. Okay, we can even use this one. So the approximation of lambda, here we call it RK, or we can call it lambda 1 to the K, right? Let me append that here. So this is also lambda 1 at the kth iteration. So it is given by this ratio. So we compute the xk's. We compute the sk's, or I can just write xk like this. It is the same thing. So this is how we generate the sequence of xk's. And then once we have the xk's, we take the projection along the entry with the largest magnitude to project. That gives us lambda 1k. Okay, so that's how we generate. So you see that mainly to complete our xk's matrix vector multiplication, which a computer program will easily do. So you see that here, in order to approximate the dominant, you don't need to go and solve. That is from linear algebra, remember, when you want to find the eigenvalues and eigenvectors. For the eigenvalues, you construct the characteristic. You calculate, you compute the characteristic equation. You first obtain the characteristic equation, which is another long process, because remember, you write that. This is what you write. If I call the characteristic matrix P lambda x, sorry. Numerically lambda, if I call that P lambda, right? It is the determinant of what? A x minus lambda x. So which in fact, no, do I really need, there's no x there. There's no x here. I just take the determinant of A minus lambda identity, like this. You see, only that's just to get the polynomial. And you know that it's not obvious to compute the determinant of this. You can easily do it when the size is 1, 2, but above that it becomes difficult. So you have to do that first, and then after doing this, you have to approximate the solution of this polynomial of that higher degree. But when I say, I'm drawing your attention to see the step that you follow in linear algebra. It will be difficult for you to do that with a computer, really difficult. But here you see you only have a matrix vector multiplication and projection. That is it, and you have your dominant eigenvector. Isn't that powerful? It is powerful. If you don't want to agree, it is. Obviously, your heart convinces you of the fact that it's powerful. Oh, when I say powerful, it even comes from power. Oh, power method, powerful method. Great. Okay, so that is it for the recall. I think stage. So far, so good. So you see that we avoid going through all that hassle. That is for the power method, not for the inverse power method. We don't obtain the sequence of xk's, right? We don't obtain it directly because here's just matrix vector, and you get it. You have your xk's. But for the inverse power method, because we are applying the power method to A inverse, of course, without inverting the matrix. Be careful. Be careful. We do that without inverting the matrix. And to avoid inversion of the matrix, what we do, at each iteration, we solve a linear system using Gauss elimination. And this will give you the smallest. Actually, give you the reciprocal of the smallest eigenvalue, and then you just take the reciprocal. Reciprocal of the reciprocal of a number is that number. Okay, so that when we say that it gives the smallest, actually it gives the reciprocal, and then you take the reciprocal to get the smallest. I hope it's clear. It doesn't give directly from here. You can see that here you have the smallest, the reciprocal of the smallest. Right? You see, it computes the reciprocal. So the result that you obtain, you take its reciprocal to obtain the smallest. Good. Please make sure you understand these steps. Very important. Okay, now today we are going to introduce another method. Shifted inverse power method. A lot of terminology, eh? I hope it will not drive you crazy, eh? Inverse, shifted inverse power method. Shifted, shift. When you want to sit next to somebody and he's trying to obstruct where you want to say shift. All right, okay, shifted inverse power method. Remember, the idea here is we want to get all the eigenvalues. We want to get all of them, but we can't. With the power method, we can't. We can only get the dominant. So, direct power method gives us the dominant. And now, by sorting, if you take the reciprocal of all the eigenvalues, the smallest now will be the dominant, if you take the reciprocal, right? The inverse of the reciprocal of all the eigenvalues will be the inverse of, or the reciprocal of, the smallest, right? Okay, now, with the inverse power method, we'll finally get that smallest. So you see that only the power method can give you the dominant and the smallest. For the smallest, of course, you need to solve a linear system. You don't apply the matrix directly to a vector to get the next iteration. But Actually, you solve a linear system to get each iteration. That's the difference. Because you're applying the power method to A inverse, but because you don't want to use the inverse, you compose on both sides with A, then it gives you a linear system to solve. Now, already the power method can allow us to get the extreme. Now, what about the intermediate values in between? Those eigenvalues in between, how can we use the power method to get those ones? That is the idea. Is it possible to use the power method and try to approximate the in-between eigenvalues, the intermediate? Yes, it is possible to do that. And in order to do that, we use the shifted inverse power method, because the shifted inverse power method is that technique that will allow us to approximate the other eigenvalues in between the dominant. And for that, of course, we have to shift. Shift. And in order to shift, we need to find the appropriate constant, because when you shift, you multiply by a certain constant and you shift, right? You need to find the appropriate alpha that will allow you to shift. It's like a translation, and we know that if you translate, you need a constant that will give you the translation move or the steps for your translation. So roughly speaking, when you hear shifted inverse power method, bear that in mind. Don't think that's something mysterious that comes from, I don't know, from another planet or from wherever. No. Once you understand power method, inverse and shifted are just modification of the power method. So they are related methods, right? Power method. All these are related to the power method. Okay, now let's look at the motivation. If you recall, for the inverse power method, the motivation was that if I know lambda to be an eigenvalue, the reciprocal of lambda is also an eigenvalue. That is the motivation that led to find or to apply the inverse power method. Because we know that if you use inverse, whatever we get is still an eigenvalue. But which of them it is, it will be the smallest. Now let's look at this theorem, theorem 321, shifting eigenvalues. Now, we suppose that lambda is an eigenvalue and V is the associated eigenvector. So we call this couple an eigenpair. This is an eigenpair of A. Now, if you take a constant alpha, then lambda minus alpha is an eigenpair of what? Of the shifted matrix A minus alpha identity. So the motivation comes from this fact. If I can shift an eigenvalue, the new shifted value that we obtain is an eigenvalue not of the original matrix A, but of the shifted matrix A minus alpha identity. So that is what we will use to compute the shifted, or to derive the shifted inverse power method. But now, in terms of which of the eigenvalue it will approximate, that is subject to the following theorem. Because the following theorem will allow us to know exactly how we can manipulate to get other eigenvalues of the matrix, right? So you see that if I obtain, I can use the same trick. I can use exactly the same trick. Once I get the eigenvalue, I can get the same trick here. See, I can use exactly the same trick here. If I have lambda minus alpha as the eigenvalue of this, In order to recover lambda, what will I do? If I apply the inverse power method to this matrix, to this given matrix, it will give us the reciprocal of this, right? It will give us the reciprocal. That's what inverse power method applied to A minus alpha will give us. So I will say power method, inverse. Inverse, if you apply the inverse power method to A minus alpha identity, this will be the eigenvector, eigenvalue that will be computed. Because remember that if for A we have lambda, inverse power method to A gives us the reciprocal. Do you understand? Once I get that, I take just its reciprocal to get lambda. So if I know this, how do I recover lambda? I take the reciprocal. So similarly here, if I apply the inverse power method to A minus alpha identity, this is the eigenvalue we'll get because the eigenvalue of this is lambda minus alpha. But the inverse power method to that will give us its reciprocal. Now, if I want to recover lambda, what will I do? Let me call this mu1, right? If I call this mu1, because when I put sub 1s to indicate that it's a dominant, right? It dominates, right? Okay, now if I want to recover that, what will I do? What will be lambda from here? It will just be 1 by mu1 plus alpha. Because 1 by mu will be lambda minus alpha. If I add alpha, I recover lambda. So that's how we manipulate to get the other intermediate eigenvalues. Is that okay? Is that clear? It's good to understand this before we dive into the theorem. You need to know exactly why we are doing it from this motivation, from this theorem of the shifting eigenvalue. Once you understand this, the theorem becomes simple. I want you to say something before I proceed. I don't want to proceed if you don't understand this. But that is exactly what we are going to do in this theorem. Is it clear for everybody? If you don't understand, please let me know so that I repeat. Because it will be of no use for me to rush when there are things that you don't understand. Because I will be thinking that we are moving together, whereas you are behind, and I will be talking to myself. Is that understood? Just remember this one. If lambda is an eigenvalue of A, this lambda is just lambda. It's an arbitrary eigenvalue. Not necessarily the dominant, just an eigenvalue, arbitrary. If I apply the inverse power method to A, I'm expected to get what? Obviously, it will be a dominant, right? It will be a dominant, right? It will give us the smallest. So this will be mu1. So that will be 1 by lambda n, if you want. This will give us the smallest, right? Because the inverse will give us the smallest. So that's what I call mu1. And then if I take the reciprocal of that, I have the smallest, right? That's what the inverse. Okay, but from this theorem tells us that if I have an eigenpair, that is eigenvalue, eigenvector, but I'm concentrating, for now, I'm concentrating only on the eigenvalue. If I know an eigenvalue lambda, this theorem tells me that if I take alpha, add to that, subtract to that lambda, it is still an eigenvalue, but not of A. Not of A, but of A minus alpha identity. Okay, actually, when whatever you have here with lambda, replace lambda with A, and when there's alpha, multiply it by identity. That's what you have here. So this will be an eigenvalue of A minus alpha identity. Now, we just assume that we are in a situation where I have identified a certain alpha, because remember that the focus here is alpha. Now, just imagine that you are in a scenario where your alpha is close to a given and arbitrary eigenvalue. You don't know that eigenvalue, but you know that it's somewhere close to an eigenvalue. And now you want to find that eigenvalue. That is the role that this alpha is playing. Right? You see that in this computation, I don't know what this lambda is. I don't know lambda. In this computation, what I know is alpha. Right? Because the the inverse power method, or let's say the power method that will be applying, the inverse power method, will be to A minus alpha identity. I don't know lambda. I don't know the eigenvalue. I know an alpha that is close to an eigenvalue, but the eigenvalue itself, I don't know it. But I only know that the eigenvalue might be around this, in this range, right? I know it's in this range, but I don't know exactly its value. So I take an alpha in that range. I take my matrix A minus alpha identity, perform power method to that. And then I perform this transformation to get the corresponding alpha lambda, the eigenvalue that is in that vicinity of alpha, will be found through this technique. So this is what will allow me to approximate my lambda. So the only thing I need here is alpha. And alpha, by this technique, will allow me to get the lambda corresponding eigenvalue. You see that this eigenvalue is not necessarily the dominant or the smallest. Not necessarily. So it is through this technique then that we'll be able to approximate the other eigenvalues. And consequently, if you apply the inverse, the power method, the inverse power method, if we know the alpha, we'll be able to approximate all the eigenvalues. We'll be able to do that. But this is long. That's why we need other method that will allow us to get directly all the eigenvalues. But for that, of course, there is nothing for free. The matrix has to have extra properties, right? You cannot perform those methods that will give you directly all the eigenvalues to an arbitrary matrix. No, you have to pay a price somewhere. Okay, is that clear for everybody? Simeon. Is it clear, Simeon? Is it clear, Janice?
It's okay, sir.
Good. Kashupi, is that okay?
Not really.
Not really. What don't you understand?
The whole theorem.
No, I'm not yet at the level of the theorem. Not yet. I'm still here. Wait. When you say theorem, you mean this shifting eigenvalue theorem? This one?
Yeah, that one.
This one, you don't understand this theorem?
Yeah, not clearly.
Okay. 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 Okay, so this is the theorem. So the theorem states that if lambda is an eigenvalue, of A, lambda eigenvalue of this. Now, for a certain alpha, alpha, this is a real number. Lambda minus alpha is an eigenvalue of A minus alpha identity. This is what it means. This is what the theorem tells us. Is the sound okay? It's as if I receive an echo. Can you hear me properly?
Yes, doctor, I can hear you.
Okay. Okay, now let us prove this. Maybe from there you will see. If you try to prove this, you will understand what it means. Okay, lambda eigenvalues of A, what does that mean? Of course, we can find V, a vector, in Rn. Of course, if this is an n by n matrix, I'll put minus 0 to indicate that this V is not 0, right? Such that when I apply A to V, I obtain lambda V. That's a definition of lambda being an eigenvalues of A. This is what it means. So this V is what we call the associated eigenvector. That's linear algebra. This is what it means. Now, let me use this same V and apply V to A minus alpha identity. Now, let me compute A minus alpha identity times V. So what is this? This is, if I expand, this is AV minus alpha V, right? Just expand, right? But what is AV? AV is lambda V. So this is lambda V minus alpha V, which is lambda minus alpha into V. So what is the meaning of this? Look at this. If you compare this with that, what can you say? I take a matrix. This is like V. V is equal to lambda minus alpha V. If I have this, what can I say? I have each time you multiply a matrix by a vector, it gives you a linear it gives you a multiple of that vector. That constant multiple is the eigenvalue of the corresponding matrix. Is this clear? If I take a matrix multiplied by a vector, it gives me a constant multiple of that vector. That multiple, that constant multiple is called eigenvalue of the matrix. So here we have a matrix. Because this is a matrix, I apply it to V. It gives me a constant multiple of V. So what can we say about this constant multiple? Alpha minus lambda minus alpha is an eigenvalue of B. What is that B? B is A minus alpha identity. That's exactly what this theorem states. Is that clear? That's just linear algebra. We are not here doing numerical method. This is a recall of linear algebra. All right. Okay, now let's go back to the theorem. Okay, now if you look at the theorem, we have a matrix A with distinct eigenvalues, lambda 1, lambda up to lambda n. And we consider one of them an arbitrary. It can be lambda 1, it can be lambda 2, it can be any of them. You see that these are not sorted. We are just telling you they have distinct lambda 1, lambda, and we take an arbitrary of them, an arbitrary element in the list of lambda 1 up to lambda n. We call it lambda j, right? Now, if you use this theorem, we know already that from this theorem, we can choose a constant alpha such that 1 by lambda j minus alpha is the dominant eigenvalue of this. In other words, we are applying the inverse power method to A minus alpha identity. Right? That's why I call it mu1. You see, I wrote it here properly. Mu1. Because if you apply the power method to something, or the inverse power method to a matrix, that's exactly what it gives us. Okay, so I did it purposely so that when we reach here, everything is okay. Right. Now we perform the power method to this matrix, or which is equivalent to applying the inverse power method to A minus alpha identity. It's the same. Remember that this is the inverse, which is equivalent to solving a linear system, right? This is a notation, but it doesn't mean that you compute the inverse. This is just a notation. It means that you solve the linear system A minus alpha identity into yk equal to xk, and you solve that, you get yk. This is just a notation. Now you perform that. Now this method is a variant of the power method that we described in the notes. Remember, I told you in the introduction that there are two types. I mean, two flavors of the power method. And this is the second, because I promised that we will be doing that later. Now here, we are still applying the power method, but differently. So once we obtain this yk, remember that in this yk, there are components, and you extract for our projection, you identify the entry with the largest magnitude, and you project along it. So instead of doing the projection, we do this directly. They are equivalent, They are equivalent. Now, the next term of our sequence, because remember that the sequence we are building are the xk, not the yks, because the yks are just like intermediate steps, right? So now, xk plus 1 will be given by this, where this ck plus 1 is the entry of yk with the largest magnitude. This is exactly what this means. Entry of yk with the largest magnitude. With the largest magnitude. So that's what I mean. See, because when we say that this is equal to yk sub j, it means that it's an entry of yk. Now this means that this is the maximum in magnitude. See, you take absolute value, the maximum of that. This is, so it is the entry of yk with the largest magnitude. Exactly what we did in the power method. You identify the one with the largest and you project. This is the variant of that method. This, for some people, is easier to perform. So now it's up to you to see which of the two is easier for you. Then you can adopt it. Right. Okay. So now you see we have two sequences that we are constructing. We have the sequence in CKs, and the CKs are just numbers. These are numbers. The CKs are numbers because the entry of a vector is a number. It's a real number. And you have the vector, which is xk. These xk's are vector. The xk's are vectors, and this is a number. So the ck will converge towards mu1, and the xk will converge towards the eigenvector v. So with this you get an eigenpair, the eigenvalue, eigenvector. The sequence of the ck will converge towards mu1. Once you have your mu1, you use this technique. Oh, why are you? Okay, this one. So this is how you recover your lambda j. Exactly as I explained here. I already explained that. That's why I took time to explain this, so that once you understand that, the theorem is just a consequence of that. Right. So that is it for the shifted inverse power method. Now, this is an example. It's already time. Do you have a class after this? Do you have a class after this? If yes, we will stop here. And then I will record another video later on or by Saturday so that you can go through. And for that next recording, I'll be talking about the example. So can we stop here for those who have class in the next session? I'm listening to you. Please say something.
Say I don't know, but I don't have class after. But say, can we not do the examples that we got last time we had class? Before we do the one of the shifted inverse theorem.
Yeah, but I want to know first if you have a class. Simeon, do you have a class?
Yeah, I don't have a class after. I don't know about the others.
Aushona, do you have a class?
No, sir.
No, sir.
Okay, so we can proceed. Okay, so what was your concern? Yes, Jonas, what was your concern?
I'm saying, sir, can we not do the examples? The example we got last time we had class. Before we do this one of the shifted inverse.
Which one? You are talking about this one?
Yeah, that one down there, yes, at 3.18.
Okay, find the largest and smaller eigenvalue of the matrix. Okay, so let's do that then. Then you have to tell me what you did in class. I mean, so let me open a new slide and write down the matrix. Six, two, two, 5, 6, 5, -5, -2, -1. Good. Obviously here okay, so the initial vector is given by -1. Oh, it was last class, not last week. Oh, the last class homework. So you have to find the smallest. I would say the dominant, of the following matrix. Using the power method. Okay, so first, lambda 1. Okay, so for lambda 1, as you know, we construct the sequence, right? We use that, we can even use the two, huh? We can use the two methods. That is the one I described in class, and the latest method, when we construct the C case and the X case, right? We can do both. But you see that it will be up to you to decide which one to use, but it's good to always expose both so that the student will select the method that is comfortable with, right? Okay, so for the dominant, lambda 1, the largest in magnitude, we construct the C case, right? We construct the C case. Not the C case, but the X case, sorry. So I would say here, first method. Oh. First method. The first method is the one that you know already. So it's good even for us to do the two methods so that you see how to apply the one for the shifted inverse power method. It's still a power method, but using a different level. So first method, we construct the sequence xk, construct the sequence, and perform projection. And that would allow us to get the lambda 1 key. So that is the projection that gives us this. This one will convert towards V, the eigenvector, the associated eigenvector. I did not stress on the eigenvector, but it also gives us both, right? It gives us eigenvalue and the corresponding eigenvector, right? So this, let me write it here. Lambda 1k that we construct will converge to lambda 1, and the xk will converge to V, the associated eigenvector. So this is important to underline, because if in a test you are asked, give the associated eigenvector, you might say that we never did it. You see, that's why I think I should underline this. The xk will converge towards that. And the lambda 1k will converge, or the rx, or the rk. This is what we call rk, right? Okay, good. Okay, so what is our x1? X1 obviously, it is a x0. And what is that equal to? Who can give me directly? Who can give me the value directly? It's -6, right?
So it's -6.
Okay, now the next one. Two.
Yes.
Yes,
it's 2, sir.
And the other one, 2 again.
2 also.
Is that what you got?
Yes, sir.
But why are you the only one to talk? What about the other students? You didn't do this. Now, what is, in which direction, along which entry are we going to project?
They are projected again with -6.
Okay, so we are taking the first component. So we do the same thing here. So that would be -6 by -1, which gives us 6. All right. Hello? What did you get? Isn't it 6?
So do we have to divide it with -1?
What are you supposed to divide with?
I don't know.
You say you are projecting. Wait. You say you are projecting along which component? The first component.
Yes, sir. Oh, okay.
So why don't you use, if you use something else, it's no longer the first component. This is the first component. If this is the first component, the first component here is -1. You are using the same phi. If you go to the note, you see that phi is in the numerator, phi is in the denominator. You are using the same phi. So if phi is along a certain direction, you do the same thing. If you do something else, you don't understand the method at all. Go and read your note, you will see that it's phi. What is this? Phi. Numerator, denominator, phi. Why should I use first component here and use a different component? Then it's no longer phi. Something is no longer phi. Phi means that the linear operator that you take here is the same here. X2. So X2 will be this by X1. Into X1, I mean. So what do you get there? Isn't it -49? 36, I mean.
-36.
Okay, quickly give me the entries of the matrix. And what is the next one?
-4.
Sorry?
-4.
And the last one?
I have -4, and then the last one is also -4.
Like this, -4, -4.
Yes.
Okay. Now, with this, what is your lambda 1, 2? You see, we still use the first component. So we project along the first component. So if you project along the first component, it still gives us, this will be -36, right? 6. Okay, have you checked these two entries? Are they, oh, wait. Let me, 2, 2. Is it 2, 2, this one? Hmm?
Says it for X? Yes. Yes, it's 2, 2.
-6, 2, 2.
Yes.
Okay, now the next one. Quickly tell me, what is your x3?
Negative 201.
Sorry,
216.
-1?
216.
-2?
16. Negative. Then the next one is -88, and the last one is -88.
Next one?
-88.
Negative what? The last one?
-88.
It's still repeating there. And now when you project, what do you get?
Negative 216 divided by -36, which is also 6.
Okay, then you stop. So it means that your dominant eigenvalue here is 6.
And how do we, if we have to get the corresponding, the associated eigenvector, which one do we choose if everything is 6 then?
Because here already you're having convergence, right? Don't you see? You're having convergence already from here. See. Okay, now in terms of the, you can take either because all these are constant multiple. They are all constant multiple. You can take the original. You can keep this one because if you say that you are taking this, if you factor this by no, you take this. You can take this one, right? You can take the first one because all these are multiples, right? If you factor this by wait, I don't really. Am I right in what I'm saying? Because if affected by 2, no, they are not exactly the same. This one. Okay, so wherever you stop, right? Like here, you can take this one. You can say after this, you can take the last one. Wherever you stop, you can take it. Because these are approximation, they are not exactly that value. If you stop here, you say that you observe convergence, you stop there. Wherever you stop, you can take the corresponding eigenvector. Like you can take this to be the approximated eigenvector. Because this is enough. We see a repetition. If you continue, you actually repeat. But since this is converging, if you proceed, it will give you a better approximation. All right. Okay, now for the smallest, you do exactly the same thing, but you'll be solving a linear system. Okay, so let's do that. Is it necessary for us to do the second method? Let's try the second method, right? Hello? Let us try the second method. You'll be learning at the same time because that's what we will use for our shifted inverse power method. So the second method, so this is the second method. First, second. Okay, so we have the second method. So what do we know for the second method? We consider the x case and what? And the c case. And the c case will converge towards lambda 1. Are we together? Are we together?
Yes, sir. Yes, sir.
Good. Now, we do exactly the same thing. We compute this y, we compute x1. X1 will be exactly this. So we see -6. Like this. And what is this? You see? So now this is our new vector that we'll be using. We'll be using this one for the next computation. Right. And this is our CK. So this is CK into, okay, that would be C1. We'll call that C1. Right. So C1 is 6. And we repeat. Now X2. A into this. So since these are the same, this is again -6 for the first entry. Are we together?
Yes, sir.
Okay, now for the other entries, what do you get? The other entry, what do you get? The second one. What do you get? -2 by 3, right?
Yes, doctor.
-2 by 3, right?
32.
Sorry?
-2/3.
And the last one? What do you get for the last one? -2 by 3 again, right? It's repeating.
Yes.
So you see that here again, you get 6. Right? So when you factor by 6, it means that you divide everything by 6. Right? So if you divide by 6, this is -1 by 9, right? Are we together? So this is C2 into this vector. So you see that it indicates that the eigenvalue is 6. Obviously, the associated eigenvector depending on where you will stop, will be this, because this is your x key here. The next x key, this is x k plus 1. No, I mean. Okay, so that's the second method. Now for, it's already 11. Okay, I will give you, okay, I will just give you hints for the next lambda n. So let's do the next one. What is the lambda? Lambda n, what is it? Obviously, when you say lambda n here, n, since we have, we assume we have, it's a 3 by 3, see, 3 by 3. So this lambda n is in fact lambda 3 because it's a 3 by 2 matrix, and n is the size of the matrix, which is 3, or the dimension Rn, n. This is 3, lambda 3. But I just leave it lambda n so that you understand it's the smallest. So how do we proceed with this one? First method. If we use the first method, obviously, yeah? Here we are using the first method. First method, we'll be solving linear system each time together, the corresponding x, right? Okay, so if you recall, in order for us to get x1, for us to get x1, right? We solve a linear system, a x1 equal to x0. Because remember, we are applying the power method to the inverse of a. So actually, ax or a1, we apply a inverse because it's an inverse power method to x0. So this is what we are supposed to write. But because we don't want to invert a, we write it this way and then we solve for x1. That is Gauss elimination, right? Are we together? To get this Gauss elimination. Hello?
So we are here.
Okay, so now, since I don't know the entries of x, I can call that x1, x2, x3, or xyz. Each time xyz, xyz, x1, x2, x3, each time, because I'll be solving that linear system. Okay, so then what do we have? So I can write here, I can just write the augmented matrix and perform a Gauss elimination quickly, because Gauss elimination, you have been doing that for many years now. Right, so you write this because if you want to solve it, it might be long. You just write your augmented matrix here. Right? Augmented matrix. Now your B is your x0, which is negative 1, 1, 1. All right. Then you perform your Gauss elimination method. Obviously, it's up to you. You can swap the rows, or you can leave it this way. Right? You can swap the rows to take this and use it as a pivot row, or you can leave this, you can fix it that, you can leave it that like that. And then you'll be using fractions. So now to avoid that, you can swap, right? So this will be equivalent to, if you don't want to be using fractions, because if you leave it this way, your multiply will be fractions, right? To be right. Now, if you want to avoid that, you can swap the first and the second row, or the last. It's up to you. So you can swap the first and the second row. 2, 6, negative 2, like this. 6, 5, negative 5, and you keep the last one, right? So similarly here, this will be 1, negative 1, 1, because you are swapping the first and the second only, right? Okay, now here you call this is your R1, this is your R2, this is your R3, right? Now, what you will do, you fix this one, you eliminate these two entries. So that's the first step, you eliminate these two, right? For that here, what will you do? You will multiply the first by 3, the first row. So here you will replace this one. You keep the row, which is R2, okay? And then you multiply the pivot row, which is the third one, by 3, and you subtract. Okay. And for the last one, you just subtract the first row from that. All right. Now, what do you have? What do you get from this? So if you perform, what do you get? So this will give you. So the first one, we fixed it already. So that is 6, 5, negative 5. And here you have your negative 1. Okay, now for this one, we know already that this will be 0, 0. Through our choice, you don't even spend your time doing the computation. Because if you do this, is because you are sure that these two are zeros, right? Okay, so now we are here. I multiply this by negative 3 and I subtract. Sorry?
Is like the first loss, is it 6, 5, negative 5 or 2, 6, negative 2?
Negative 2, sorry. Thank you.
No, I mean like the whole low there. Was this not supposed to be 2, 6, then negative 2?
I think I copy here instead of copying here. I copy from the first matrix, sorry. I copy from the first augmented matrix. So it is 2, 6, negative 2, and then 1. Correct, thank you. So we multiply by negative 3. This will become negative 18. So 5 minus negative 18, what is it? Negative 13, right? Are we together?
Yes, Doctor.
Okay. Now the next one, this will be 6. This will be 1. Are we together? You should be proactive. Nah? Don't spend that much time. And this is negative 4. Are we together?
Say we are together.
Is that correct? You are not saying anything, eh?
Yeah.
Okay. Yes.
No, say it's correct.
Yeah, but you should be talking. Okay, the last one we just subtract. So I take this one minus that one, which is negative 1, like this. And then this one minus that, right? That will be 1. All right. And this will be 0. All right. Okay, now the last step is to 0 this entry. Okay, So to zero that entry, what should we do here? Now this is our new pivot row, R2. We have R2, and this is our R, and this is our R3. Right, so we concentrate here. So for this, so we have R3 minus what? Negative 1 by 13, isn't it? Okay, because I want this to be negative 1. So this is what I will perform. So this is our multiplier. If I take the reciprocal of that and multiply, that is negative 1 by 13. And then I subtract, I get the answer. Okay. Are we together? So if I do that, I have 0 here. So here we have, for this last step, we have 2, 6, negative 2. And then this one is 0, 0 here also. And then we have negative 13 here, 1 here. This is 1, negative 4 for that. This is 0. Oh, 3. 0. Okay, so now what would this last entry become? If I multiply the way I said, this is 0. So I'm multiplying this. So this would be 113. Look, if I perform this is 113. Right? So that would be 1 plus 113, which is 1413. Right? So this is 1413. All right? Are we together?
Yes, sir.
Sir,
Oh, look,
I
this is
have
plus, huh? This one is plus, sorry. This is plus. This one should be plus. Okay. This
doctor.
should be, yes.
I have a question. What if we make it
It should be like this.
13
It should be like this. So there should be a minus here. Right. It should be like this. So this is 12 instead of 14. Right. Okay. Where were we? Yeah. So we are done with this one. Now, finally, the last one. This is already 0, so I will not perform anything here. So that would be 4, 13 here. 4, 13. Okay, now if we perform back substitution, So directly we can get the value of x3 here. What is x3? You say I cancel this, like this, I cancel. And this is 3, right? That's 1/3. All right. So that's your x3. And then you proceed to get your x2. And then x1. Using your back substitution, I will not do that. So once you do that, you get this will give you the component of your x1. This one. And you project and you proceed. Okay, so we will stop here. You can do that yourself. So that's the procedure. Okay, so we have exceeded at the same time. Since we started late, I think we already covered over an hour. Okay, so we stop here for today. Please do the rest of the computation to convince yourself. From the first method, oh no, this is still the first method. Okay, so just do that. The most important thing is to know that you are solving a linear system, and that's how you'll be proceeding. Right. But in a test, you will not be asked to perform too many operations because it's a bit time consuming to perform that. If you have to do that for 4 or 5 iterations during a test, is too long. Maximum will be 2 iterations, right? Just perform your gas elimination and then you get the result. Okay. If there's no further question, we'll stop here. Okay, thank you so much for your kind attention. God bless you and see you next week. So have a happy math weekend. Happy math weekend, meaning that over the weekend, do your maths. Read the notes, do the tutorial. Okay. Shalom.